Welcome to part 3 of 202E. So far, we've looked at basic RLC parallel circuits containing a resistor, a capacitor, and a pure inductor. Then we went on to look at circuits that contained a heater and a motor. Now, we're going to look at multiple motors connected in parallel. We have to remember that since the motors can be treated as an individual series circuit, we must solve each branch separately. Once we have each branch solved, in order to find out what the current for that branch is and what the Z value of that branch is, we can then apply parallel rules to solve for the total circuit. Let's look at this example from your module. We have two motors that are connected in parallel. We've been able to measure the resistance of each of the motors and calculate what the inductive reactance of each motor was. From here, we can create impedance diagrams for each individual motors as they are a series circuit on that branch. The goal is to find the Z value. For motor number 1, I have a Z value of 29.7 ohms at 58.5 degrees, and motor 2 has 26.7 ohms at 36.7 degrees. Now that I have the Z value of each branch, I can continue on to find my total current for each motor as well. For here, I'm going to use Ohm's law, which is the applied voltage of 240 volts divided by the total Z value to get 8.1 amps at 58.5 degrees lag for motor 1 and 9 amps at 37.6 degrees lag for motor 2. Since my two motors are operating at different angles, I can't just add them together. I have to add them together vectorially, meaning I have to use my HV chart. To use the HV chart, I will take my ampacity, multiply it by the cosine of the angle in order to get the horizontal component of each branch. Then I add those two branches together to get a total horizontal component of my complete circuit of 11.4. To get my vertical component, I have to take the ampacity, multiply it by the sine of the angle in order to figure out my vertical component. Keep in mind that every time that you put the angle into your calculator, you should make sure you put in the negative as well. It's going to show up in the vertical component, showing that they're lagging verticals. When I add all my verticals together, I get a total vertical component for my complete circuit of negative 12.3. The next thing I can figure out from here is what my I total is going to be. To find I total, I'm going to use Pythagorean's theorem again. The square of H plus the square of V, when you square root that, will give me my I total. In this case, my I total is going to be 16.77 amps. We can see here why the angle matters. If I had just added the ampacities together, it would have been 17.1, whereas I am significantly lower than that to what my true ampacity is going to be. Now that I know what my total current is going to be, I can focus on the angle for my total circuit as well. I use my tan formula for this being opposite over adjacent. My opposite value is my vertical component. My adjacent value is my horizontal component. So negative 12.3 divided by 11.4 gives me a value of negative 1.079. To find the angle from that number, I have to do inverse tan, which gives me an angle of negative 47.17 degrees, or 47.17 degrees lagging. To find my power factor, I want to cosine that angle. So the cosine of negative 47.17 degrees is 0.68 lag. And this is what my power factor for my complete circuit is. Now I have found the total ampacity for my entire circuit as well as what my power factor for this circuit is. This circuit should draw 16.77 amps, and if I were able to measure it, I would have a power factor of 0.68 lag. You'll notice that if I simply added the two ampacities for my two motors together, I would have had 17.1, but 16.77 is what I should be reading on my ammeter if I were to clamp these two motors together. This is why it's important to make sure that we take into account the angle that the motors are operating at, because it does change our final numbers, and it could mislead us if we're not ready for that. This brings us to the end of Module 202E. We should keep in mind the outcomes that we wish to achieve for this module. First, we analyzed the circuit containing resistance, inductive reactance, and capacitive reactance connected in parallel. We then applied those concepts to a parallel circuit containing a heater and a motor, and then further developed them by solving problems including multiple motors connected into parallel. You can now return to Blackboard to complete the worksheet for this section. Review the understanding with the knowledge check and then also do the 202E review test to put all three of these parts together. After you've done this, go ahead and move on to 202F.